So the so the first announcement is make sure you fill out the course surveys. So this is always very useful for me, and I will read all of them. And of course, you can also email me directly. But if you fill out the surveys, it goes through the system, and it's always useful. Constructive criticism is always appreciated. So how to make it better for next time, you know. So it takes only a few minutes, so definitely do it if you get a chance. Okay, so today is really the last lecture of the semester, and we're going to talk about luminescent concentrators, primarily applied to solar, but also a few other interesting applications. Today's lecture will be somewhat short because single topic we're going to cover, but I want to make sure if you have questions about assignment, the last two assignments, I will be around so we can discuss those as well. So please remember that Thursday we have the presentation, which is assignment 4, and which is the detailed instructions we went through in the last class. So if you have any questions, let me know. Yeah. Yeah, it's probably 5 should be due December 6th. Yeah, assignment 4 is assignment 4 is just a presentation in class, so you don't need to submit anything. Assignment 5 is where you have to submit these two things, which is the short video and the business canvas. Initial and final. Sorry. Yeah, a few minutes. I think I said less than 3 minutes. Yeah, minimum? No, no. I mean, yeah. No, I mean, you can make it as short as you want. Yeah. Okay, great. And of course, I'm recording the lecture, so that's why I'm wearing this. Okay, so let's jump right in to luminescent concentrators. So luminescent solar concentrators are essentially an approach to making, so we talked about solar concentrators in CPCs before, where we collect light from a large area and assign it to a small device. And the idea is that the device itself is much more expensive than the optic. So you can get a small, high efficiency device at a lower cost, but still collect light over a large area with a cheaper optic. Now, luminescent concentrators, and one of the big challenges in regular concentrators is tracking, right? If you recall, when we had CPCs, we know, or any sort of concentrator. So we had a CPC, which kind of looked like that, solar cell. Light coming in directly is collected, but if light comes in outside the acceptance angle, it's of course escapes the system. It's not collected here, right? So we had the efficiency function where it's 100% and then it drops off where the acceptance angle is, right? Now, this is of course a problematic because that means you have to kind of track the sun very precisely depending upon the concentration. Luminescent concentrators was an approach that was proposed to overcome this challenge and also to make things much cheaper. And the idea is relatively simple. The idea is to, the vision is to essentially take windows on buildings, for instance, and turn them into solar cells. So the light comes in, it is somehow absorbed in the glass or a portion of the light, okay? And it gets trapped in the glass and gets guided to the edges of the glass, and the solar cell is placed, or an absorber is placed at the edge of the glass to absorb the light and convert to electricity. Of course, you want the visible portion of the light, or the vast majority of the light, to pass through so you can see, right? So imagine converting this window into a solar cell where you want to be able to still see outside, but you want to collect some portion of the light within the glass to be collected into a solar cell. And we'll see how that works and what the limitations are. But that's the vision. The idea is to have a building integrated photovoltaics of course, it has to be cheap, right? Because glass is a lot cheaper than a solar panel. So you want to make this as cheap as possible as well. This is big industry today. For instance, there are companies like 3M, which sells devices along these lines. There's a few other smaller companies as well. It's a bit more popular in Europe. You don't see so much in the US. So the motivation of doing this is to reduce costs, because again, the key is that the glass is much cheaper than the solar absorber. So the glass can be large area, collecting light over a large area. Solar absorber is small, it's only sitting at the edge of the glass. Okay, so that's one. Number two advantage is that you can potentially increase efficiency, and we'll talk briefly about it, by collecting more of the sunlight than you would with a conventional solar cell, which is of course a little bit problematic, as I'll mention later on. And the two other advantages are you can integrate with buildings and potentially do non-tracking concentration. So how does this work? This works in a very simple sense. As follows, and we'll look at it in a bit more detail. So imagine a piece of glass. Okay, now this is a very special piece of glass. It's embedded with certain molecules that will absorb the light. Okay, glass by itself, of course, is transparent. Nothing light passes through. So here we have little molecules which are embedded randomly. Okay, these are called chromophores, or it's a sort of like a fluorescent molecule. Light comes in, sunlight comes in. It can come in any direction. So that's why tracking is not important. Gets absorbed, not by the glass. Glass is transparent, okay, but by these molecules. So let's say this molecule absorbs the light, and it will get to an excited state, and we'll talk about that, and it will relax and emit a photon. Okay, it will emit a photon. This photon, if it's emitted at an angle which is within the critical angle of this glass, will get trapped. So I'm going to draw a ray now. Okay, if this angle is now greater than the critical angle, which, if you recall, the refractive index is 1. This is sine inverse of 1 over n. 1 is air, n is refractive index inside the glass. It can be plastic, by the way. Anything that's transparent will get totally internally reflected and guided to the edge. Okay, just like a fiber. And here you will place a solar cell, which will absorb that photon and convert to electricity. That's the idea. Okay. So of course, if you put lots of these molecules, you'll absorb lots of the light. However, if you absorb too much of the light, then you don't get much light going through, so it's not a good window. So it really depends on the application, how many molecules you put here to do the absorption. There are other problems that happen as you increase the density of these molecules as well. We'll talk about that. So you can see this somewhat in this picture. So you can see, let's look at this piece of glass here. Light's coming in, okay? It's absorbing the light, let's say it's white light, and the molecule's emitting red light, and that's getting trapped and guided to the edge, like here. And that's why you see the edge of this glass is glowing red, because that's where the light's coming out. If this glass is very clean and smooth, no light will come out from the top. But if it has scratches, you will see them coming out as well. Okay, but you can see it's bright here, and then you can also change the color that the light's being emitted by changing the molecule that you put in here. Okay, this can be chemically synthesized, can be yellow, green, blue, and so on and so forth. So one obvious application for something like this is displays, right? If these molecules can actually emit in all these colors, you can get displays with lots of colors, which is a very nice application. And there are companies which do this, and they use, typically, instead of using organic molecules, they use something called quantum dots. Quantum dots. There's a company called QD Inc., I think it's called. Something like that. Anyway, they make quantum dot based displays. It's also very similar to the organic LEDs that you hear about nowadays in Apple Watch and so on, right? Some of the phones screens. It's very similar related technology. But of course, this is kind of where it I would say, originally started from. One of the ideas, anyway. Okay, so let's think about what is the concentration here. So let's do a quick practice. Okay, so maybe you can discuss with your neighbors. Let's imagine a window of size 1 meter by 1 meter, whose thickness is, let's say, 1 centimeter. They're pretty normal, right? Or a windshield of a car, whatever. Okay, and let's imagine we have solar cells all across the perimeter. What is the geometric concentration factor? It's like we did for the CPC. Go ahead, give you about a minute or so. You can discuss, obviously. Don't ask Steve. You can ask him. Mario, you guys can talk. So first of all, remember what is concentration factor, right? What does this mean? Okay, what does this mean? It's a ratio, right? The numerator is how much you're collecting. What is the area? Yeah, let's call it input area, right? And the bottom is the output area. And just to remind ourselves, we've done this many times before. For the CPC, remember it looks kind of like that. This is the input, and this is the output. Now we just have a different kind of concentrator, so just try to identify what's the input, what's the output. Okay, I'll let you think for a little bit. Yeah, now you're on the right path. I didn't do the numbers, but as long as you know what to do, it's fine.
Yeah.
So the input, of course, you know, if you think about the window, the input is just the area of the window, yeah? So light's coming in, going in. Let's just assume it's only coming in one way, not both ways. I mean, you can have both ways, but let's just, for the sake of argument. So the input is simply 1 meter by 1 meter, right? So the numerator is 1 meter squared. The denominator is the output. Now the output, as I drew here, is the edge, right? The solar cell, and you have to make the assumption the solar cell simply fills the entire thickness. I didn't tell you that, but to make that assumption. So that's the output, right? So this thickness is now 1 centimeter, but it's all the way around. So 1 centimeter times the perimeter, which is 4. So 0.01 times 4, 0.04. So the top is 1, bottom is 0.04. Is that correct? Right. Okay. 10. So this is what, 25? Okay.
You don't have to consider the length.
Yes. So that's this 4. 4 meters. 1 plus 1 plus 1 plus 1.
Okay, I see.
Yeah. And this is just the width. So this is the area of all the solar cells all the way around, if you do it all the way around. Typically, of course, you don't put it all the way around, you only put it on one side, and you could put reflective surfaces on the other sides to collect the light. Okay, so one obvious thing here is that how can I increase the concentration factor? Because that's kind of generally the goal, right? We've been trying to do. What can I do to increase the concentration? Bigger window and how? Ah, that's a good point. Yeah. But change the. Oh, you mean reduce the perimeter somehow? Yeah. 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 You can also reduce the thickness. Yeah. 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 Good point. Yeah. That's what I was thinking about. So can I? What is there a limit? Let's ignore that for the time being. But is there a limit? Can I just keep making it kilometers, miles, infinite? Huh? Yeah, yeah. It doesn't cost anything. Yes, let's say. Yes, absolutely. Yes, because you're correct. Good intuition, good insight. Because it has to do more bounces if you keep increasing it, and we'll talk more about. There are more problems. But generally speaking, if I give you this problem, everything was perfect. I can have infinite concentration, which of course is breaks the second law of thermodynamics. Not possible. So we'll talk about why it's not possible. One of the reasons is what you just mentioned. Okay. So let's see how we can model this in a bit more careful manner. So it's also called the luminescent solar concentrator, or the LSC. It consists of a transparent material, okay, glass, plastic, whatever, that has been doped with a fluorophore capable of absorbing the incident solar radiation and emitting fluorescent photons. So a few things to point out here. So you want these molecules to absorb all the wavelengths of sunlight, right? As many as possible. So you do some chemistry to make this as wide an absorption band as possible, which is quite challenging actually. And of course, when you emit it, the light that's emitted ends up at the solar cell. That's what's absorbed by the solar cell, right? But you don't want that very broad. You want that just in the perfect wavelength where you can convert the light to electricity efficiently. So those are the parameters that material scientists and chemists try to optimize for. You want to absorb everything by this molecule and emit only in that narrow band where whatever cell you're using can convert the light to electricity very efficiently. It's a very challenging proposition, but lots of people work on it. The other advantage, by the way, to do this is that you can make these things very flexible, right? So it doesn't need to be a window, it can be a flexible sheet. So there was a company in Massachusetts called, I think it was, I don't know if it's still around, but called Konarka. They used to make these flexible solar cells as facades for bus stops and things like that. I'm not sure if they're still in business, but they used to be making them. So now let's look a little more at just the geometrical optics. So again, this is something we've actually addressed before, but so I want you to think about it also just briefly. Light comes in, a fraction of it gets inside. Of course, some fraction is reflected off the top, as we know. We can put an anti-reflection coating, as we've talked about before, if you want. And then it refracts in, gets absorbed by the molecule. The molecule, of course, emits in all directions. It has no preferential direction, okay? So it's isotropic. Which at any instant of time, of course, it emits a photon, but that photon can go in any random direction. So averaged over time, it emits in all directions. This is a way to think about it. And then let's consider one of these directions, okay? And if this angle is larger than the critical angle, it's reflected 100% and gets trapped and goes to the solar cell. The question here is, under ideal conditions, what percentage of the emitted photons are trapped by the total internal reflection? We've actually done this before. So this is the review. So you can just think about it and discuss it briefly. How would you answer this question? I don't remember if it was in the quiz, but maybe something similar was. Go ahead. So again, what am I asking here? This molecule is emitting light in all directions, but what fraction of that light is trapped within the glass? This is what I'm asking, right? What percentage of the emitted photons are trapped by TIR, which is total internal reflection, okay? Just remind ourselves. I know we might have forgotten, but that's okay. I don't expect you to remember everything, but at least you should know the concept so you can think about it and try to answer. The steps are more important, right? So let's think about what does trapping mean. Again, this angle must be greater than the critical angle. If this comes in at an angle that's less than the critical angle, what happens? It goes up, right? It escapes. Larger angle. Refracts out. So this is useless. It's lost, not within the system. So we just have to find out, okay, how many rays will satisfy that condition, right? How many rays will satisfy the condition that theta is greater than theta c, or theta is greater than sine inverse of 1 over n, or in other words, what is the ratio? So of course, this is a three-dimensional angle. There's a solid angle here corresponding to theta. What is the ratio of that related to the whole sphere, right? So you have some solid angle, which is within the escape cone, divided by 4 pi, which is the total. That's the probability that it's trapped, right? And this, I forget the exact expression, but we've done it before. It's something like 1 minus square root of 1 over n squared or something like that. Anyway, you can go back and look at it. But that's how you would approach the problem. Okay, I think it might be in the next slide. Let's look. But it's okay, right? We have done this before. Everyone should be familiar with it. So that's the first, thinking about loss mechanisms. That's an obvious loss mechanism, right? I'm not collecting 100% of the emitted photons. So that's not good. How would I increase that, by the way? How would you minimize this loss? Any ideas? You can roughen the surface, which is a good point. That will do light trapping. So you will trap more of the light. But there is a problem here in the sense that if you roughen the surface, it won't be transparent to you as for a window anymore. It'll look like frosted glass, which might be okay for some applications. That's a good idea. Anything else just from looking at this? Remember, this cone angle divided by 4 pi is all I'm collecting. So to increase my collection, I can increase my cone angle, right? Larger the cone angle, I collect more. How would I increase the cone angle? No, this location doesn't matter, right? It goes by angle. How would what determines this cone angle? Yeah? No, because all the molecule is doing is absorbing light and emitting in all directions. It has no control over where the light's going. What I'm asking is, how do we control the cone angle? The molecule, let's say, is randomly distributed. It doesn't matter where it is. That's correct, but I'm asking a slightly different question. I'm asking, how would we increase this percentage? That you cannot change by changing the molecule. Now you can change the absorption and the emission wavelengths, and we'll come to that. But think about what determines this cone angle? This critical angle, right? Right? This angle has to be larger than the critical angle in order to be within that cone and be reflected off, larger than that cone, right? So if I want to prevent the ray from escaping, I can reduce the critical angle. That means I'll collect more of the light. Does that make sense? Okay. What I'm saying is, if this ray is trapped and this ray is not trapped, if I want to trap this ray, I could simply engineer this material such that this critical angle is smaller. It's a property of this host material, not the molecule. But what property? What determines the critical angle? Yes, exactly. The sine inverse of 1 over n, right? Sorry, I guess you can read my thing. So if I wanted to decrease that, I can. What do I do to n? Increase or decrease? Okay, if I increase n, what happens? 1 over n decreases. Sine inverse of 1 over n decreases. Correct? So I need a higher index material. Higher index glass will reduce that loss. But of course, higher index glass is more expensive and more complicated. But okay, something to think about. Okay, I guess everyone forgot quite a bit. What's that? Not always, but in some situations, yeah, getting higher index, not a question of just money, but also how you process it. Sometimes if you increase the index of glass, for instance, my glasses here have very high index. That's why I can be very thin, because my eyesight's very bad. I need a lot of refractive power here. So generally would have been very thick maybe 10 years ago. But nowadays we have high index polycarbonate, which allows me to get very thin glasses. Okay. However, it's hard to process it, so it's expensive. So it's a good example. It's not just the material from, but how you process it as well. Anyway, so so what are the different challenges? Why is this not so widely used, this idea of luminescent concentrators? So we'll talk about this. One of the problems is what we just talked about and what you were pointing out before. So one of the big issues, of course, is low efficiency, because these molecules, remember, they have to absorb the light and re-emit the light, which is not a very efficient process. Like it's a fluorescence. Fluorophores are not very efficient. They tend to be organic and so on, which means that they degrade over time. So low efficiency is one problem. The other problem is, if you think about, is photostability. And this you might have seen before. So some of you are familiar with transitions glasses, right? Glasses which become dark when you go outside. They become transparent when you come inside. In fact, my glasses used to be like that. But over time, those molecules degrade, and now it's no longer transition. Okay? So with enough bombardment of the UV rays from the sun, these molecules degrade over time. So in exactly the same way, these molecules, which are embedded here, will slowly degrade over time. And degrade means that they may not absorb the light as efficiently, they may not emit the light as efficiently. They just degrade. They're typically yellow. So these plastics, for instance, the glasses, they become slightly yellow over time. So that's what's shown here, which is time on this axis, and short circuit current density on the top axis. So in this case, it's talking about an organic solar cell, but basically the same thing happens in those emitters as well. So you can see the current density drops, and the rate at which it drops changes with temperature. That's all it's showing, is at higher temperatures, it drops really fast. Lower temperatures, it drops slower. Okay, which is also expected because organics can degrade faster at higher temperatures. But something to be worried about, especially in the sun. So concentration onto organic dyes may not be very good. There are lots of new materials being investigated to solve this. Like I said, quantum dots are obvious ones. There are lots of companies and research groups looking at it. There are rare earth materials which are used in laser dyes and things like that. Semiconducting polymers and things like that. Okay. But can you think of some optical solution here from whatever we have talked about in this class of solving this problem, just conceptually? Drop something. So the problem, let me reiterate what the problem is first. The problem is that these molecules will degrade over time because of exposure primarily to the UV rays of the sun. So how would you prevent or mitigate that degradation optically? Any ideas? Correct? It's a good idea. Yeah. One obvious one is that I said UV is the primary culprit here. So you could try to put something on top here that prevents the UV from coming through or minimizes it or deflects it or whatever. Like a sunglass, right? That's one option. You could cool it, right? You saw temperatures, cool it, so on and so forth. Okay? Keep going. In order to quantify the performance of luminescent concentrators is something that we have to analyze, but we analyze this conceptually. Something called the Gutzberger efficiency equation. Gutzberger is a guy, I believe from Austria, who first studied these things. So the efficiency of a luminescent concentrator, which is shown on the top there, eta LSC, is essentially a product of a bunch of loss mechanisms. And we'll look at each of these loss mechanisms conceptually, okay? So you just need to understand them from an intuitive perspective. It's essentially a product of the efficiency of various things that can happen in the system. We'll talk about each of them. So the first term here, 1 minus R, is very familiar to us. It's just a fraction of the incident light that is transmitted into the sheet. R is the reflectivity of the glass. So as we know, light coming in here, a portion of it gets reflected back, a portion of it gets refracts in, and how much is reflected and refracted in depends on the refractive index based on the function equation there. We've seen this before, right? R is n minus 1 squared by n plus 1 squared, which is the reflected light. 1 minus R is what's transmitted. So this number is about 4% for glass, refractive index 1.5 in the visible. So 96% of the light goes through, okay? Pretty simple. Of course, we know how to increase that by using anti-reflection coating. We talked about this before. Then the second factor here, PTIR, is what we just talked about 2 slides ago, is the probability of the total internal reflection. Now, how many of the photons will remain within the cone and be trapped versus the photons that are outside the cone and be trapped and within the cone and escape. And if this is what we were talking about before, if the critical angular side inverse 1 over n, the probability that's trapped can be approximately calculated square root of n. 1 minus 1 over square root of n, essentially. Square root of n squared minus 1 over n, okay. This is basically the same equation as we saw before with the solid angles. If you run the numbers for 1.5, this is about 75%. So roughly 75% of the light is trapped within the glass, okay? We'll talk about reabsorption in a second. Eta absorption, which is the third term on that long equation, is the absorption efficiency, which is how efficiently will the molecule absorb the incident light. So let's think about that for a second. The LSC, the molecules that make up this LSC, must absorb the greatest possible range of wavelengths with the corresponding photon energies greater than the band gap of the cells used. What does that mean? That means the molecule must absorb as much light as possible, and when it emits the light, these, what I drew with the blue, must have enough energy to be absorbed by the solar cell that we're using. If it doesn't have the energy to be absorbed by the solar cell, then it just passes through the solar cell, right? It's useless. So that's why I was saying before, the design of these molecules is, of course, pretty critical. So let's assume we are using a silicon solar cell here. And in that case, the LSC must absorb all the wavelengths let's say less than 950 nanometers, which is roughly the band gap of silicon, those photons will have energy higher than the band gap of silicon. And you want it to emit close to the band gap because we know that's where silicon absorbs most efficiently. So emission should be roughly 950 to 1000. So it gives you a prescription to do the design of these molecules. So of course, this eta absorption is now determined by chemistry or material science if you're doing quantum dots. So this is where a vast majority of the scientific work nowadays happens. And a good number, exemplary number, is about 70% or so. Okay, so far we've had, let's keep a tally. We started with what, 96% in the reflection? And then what was the previous one? I forgot, 70%? TIR was 75%? Yeah, okay. So we started with 96 and 75 for TIR, multiplied by, what did I say, 71 for this? Okay, let's keep going. The next term here, eta PLQY, is PL is photoluminescence, QY is quantum yield. So it's a photoluminescent quantum yield, can also be called luminescent quantum yield, fluorescence quantum yield, and so on. This is determined by quantum mechanics, so you don't have much control over it. There's a little bit of control. It is essentially the probability that an excited molecule, we call it a fluorophore, will decay by emission of a photon. In other words, the light that's absorbed by this molecule will then result in the emission of a photon. What is the probability of that happening? Because there are many other things that can happen. The molecule can absorb the light, and instead of emitting a photon, can simply create vibrations in the structure of this matrix of the glass, for instance. Okay, it's called thermal loss, for instance. We can do lots of things, and this is a very important parameter that's primarily also controlled by the chemist or the material science, but with not as much control as before. Okay, how do you calculate this? It's pretty simple, conceptually anyway. It's simply the number of emitted photons divided by the number of excited molecules. Okay, so let's say you have a million molecules that are all excited, and you got 10,000 photons. It's 10,000 divided by a million. Okay? On an average, so this is all statistical, right? Ideally, you want this to be as high as possible, of course, and that's a good number, 95%, if you have a very, very nice dye. So it's 95%. The next term is what's called a Stokes efficiency. Eta Stokes, and some of you might know this. And typically its value is 75%. Let's see what it means, but let's write that down. To understand what Stokes efficiency is, at least conceptually, from an engineer's perspective, we have to look at what's called the energy band diagram, okay? To understand what these molecules are actually doing. It's this highly simplistic understanding, but this is good enough for us. The molecules typically exist in something called a ground state. They're relaxed, okay? Not always, but we're going to assume that for the sake of simplicity. The photon comes in, this is sunlight. The molecule absorbs this photon, gains energy, means it goes up in energy. So this energy, this axis is increasing energy. It jumps up into a higher excited state, which has higher energy levels. And by quantum mechanics, it actually relaxes very, very, very quickly to the band edge, very similar to a solar cell. So you saw this in a silicon solar cell, for instance. But in a molecule, it's a little more complicated, but very similar idea. This does not emit any photons. This is simply thermal loss. Mostly losses heat. Then this molecule relaxes to the ground state, and in this case, it can emit a photon. This is the emission we are most interested in. Okay, so you saw that the light that came in, that this absorbed, this arrow is longer than this arrow. Okay, why? because I have undergone this transition here, which doesn't emit any photons. This transition is a loss. Remember, this is the energy that I want to capture and convert to electricity, but this is absorbed, but I only ended up emitting this much, which is this much, slightly less than before. And this loss is referred to as a Stokes loss or a Stokes shift loss. Yeah.
The Stokes in Raman,
Yeah. Yeah. Yes. Yeah. Yeah. It happens in any well, any two-level systems actually. Yes, but anti-Stokes is something different because you have to pump in energy. Yeah. So we won't talk about that. Okay, but it's pretty simple, right? You absorbed so much light, let's say 100 joules, but you emitted only 90 joules, approximately. That's the way to think about it. And how does this manifest itself in the light? Yeah. Yes, correct. This is a sort of inelastic scattering. Raman is an inelastic scattering. This is also scattering, right? You can think about it as scattering, but it's inelastic scattering, where the energy of the scattering particle has changed. They're all similar. Right? Now, how does this energy difference manifest itself? It manifests itself in the color of the light. Remember, we saw in the very first slide all these glass plates which are exposed to sunlight and it looks green on the side. That shift in color to go from white or blue to green is this. And we can see that in the wavelength. So the excitation, which is also the absorption of the light, happens in the blue. So this is 450, now maybe 485 or so, that's blue. But the emission happens a little bit in the green, in this case, 530. Of course, in an actual molecule, these numbers can all change, but this is an example. So absorbed in the blue, emitted in the green. As shown in this picture, of course, absorption is in the green, emission is in the red. So that shows the change in color. So now remember what we're trying to do again, the big picture. We're trying to collect this in a solar cell. You want this light to match the highest efficiency with which the solar cell can convert into electricity. That's very important. This, of course, you don't care particularly, except that you want to absorb everything as much as possible. However, that's also very difficult to do, to absorb a lot, because you can see this is a very narrow band, right? If you come in at different wavelengths, it won't get absorbed. So to account for that, people try to design multiple molecules. So you can have many absorption bands. Exactly, yes. So in a dye-sensitized solar cell, the principle is very similar. Instead of emitting the photon, you leave this as not an electron hole pair in that case, it's an exciton pair because it's not exactly an electron and a hole in the case of a molecule. And that goes to the terminals and draws a current. So this is exactly a solar cell, right? Very similar, except for this. You don't want a solar cell to emit too much light. Although, as you probably saw in James's lectures, a good solar cell is also a good LED. Has to be a good LED from thermodynamics, actually. Right? This is an LED, right? Emitting light. This is an OLED, organic LED, exactly the same thing as what you see in some of your Samsung phone and Apple Watch and so on. Exactly the same thing. No. Their band gap is always better for both. This is why the gallium arsenide cell, which has a direct band gap, gives you much higher efficiency because you don't need to match momentum. You automatically match the momentum because of minima and we are going a little bit off track. But I don't remember if Surangsu talked about this, but okay, so we can talk about it at the end. But a direct band gap material, so gallium arsenide gallium nitride, for instance, is what's used in LEDs, right? Because the direct band gap material. Okay, So we're going a little bit off topic here. Putting it all, what's next? Okay. So we are Stokes Ada host. That's the next one. Host efficiency. This is the loss from absorption of the trapped fluorescence by the host material. In other words, this blue light that's emitted here, I'm drawing this as passing straight through, but this material itself, the glass might absorb some of this light, right? Because it's not perfect. There might be some scattering or some defects and so on. So you have to account for that. And if you use polymers, of course, they absorb in the near infrared. So if you use PMMA, which is plexiglass, this efficiency is about 95 to 98%. So this is our 98%. And then what's next? ERA TIR, which is the efficiency of TIR, which is kind of a weird thing to say because total internal reflection should be 100%. But of course, as we know, no surface is 100% smooth. Right? If you have some roughness, some of the light escapes. So this is theoretically 100%, but generally speaking, very close to 100%, let's say. So we're going to leave that as 100%. What's the last one? Era self-absorption. Okay, this is an important point. We didn't talk about this. So here, when the light is emitted by this molecule, what happens if this emitted light encounters another molecule? Yeah, it is a form of interference, but what will happen? So the molecule, there's a photon coming through. What will happen to it? Well, there are several things that can happen. Nothing, for one. Maybe the light just passes through, which is good. That's what you want. But it can be absorbed again, as I said here, reabsorption. Yeah. When you say combine, one is matter, one is a photon. When you say combine, it's absorbed and it gets excited state. That is reabsorption. Well, one is a molecule, one is a photon. So two photons will interfere, but a molecule and a photon cannot interfere. They cannot get absorbed or scatter or something like that. Yeah.
So it'll be like chain reaction in reverse.
Exactly. Yes.
You're gonna have less and less energy.
Correct. Exactly right. Yes. Exactly. So if that light gets reabsorbed by another molecule, that's a loss, right? Doesn't reach the solar cell. It's absorbed again, unless it re-emits. But of course, that's a lossy process. Remember the Stokes shift and all that? And this is what limits us, in addition to what you said, from getting infinite concentration. So think about making this huge. Photons have to travel a long way to reach the solar cell. The probability of reabsorption will kill you, because at some point everything will get reabsorbed if you make it very large, right? This is in addition to what you were talking about before. Okay. So this again places a constraint on how you, as a chemist or a chemical engineer, design these molecules. Right? You want to minimize that reabsorption. Again, very challenging to do, almost impossible. But the other thing also to keep in mind is that if I want to have lots of absorption, I want to increase the density of these molecules in here, right? I want to put it back in as much as possible. However, that's also bad, because then there's a probability that if the emitter light will see another molecule and get reabsorbed. If I put too many molecules here, there will be higher chances of reabsorption. So these are competing requirements. Okay, so again, another design parameter to think about. So this is self-absorption or reabsorption. This is a fraction of fluorescent photons reaching the edges of the LSC sheet, luminescent concentrator sheet, without being lost due to reabsorption. This depends on the dye concentration and quantum yield, which is basically what is after emission, what is the fraction of the light that reaches the solar cell? Okay, and that really depends. It has a very large variation here, 40 to 80% based on concentration, dyes, and dye quantum yield, and things like that. So let's say 80% there. Okay, I think we have gone through all of them before I do that. So now we can multiply them all together. Let's see what we get. Can someone do this quickly? All right, let's say 29%. I don't know if that's right, because I haven't done it, but roughly right. Okay. So you can see, although each of these is pretty big, pretty nice, high efficiency, once you multiply them all together, you get a pretty low number. Okay, you lost over 70%, over 80% of the light. And not over 80, sorry, over 70% of the light. Okay, so it's not a very efficient process, right? Of course, this equation also gives us a prescription on how to increase that efficiency. That's a very challenging problem. This is one of the main issues, in addition to the degradation problem, that hasn't been widely adopted. But it's important, it can be adopted for various niche applications, so on, like I said, for flexible solar cells, building integration, things like that. Okay. Now let's talk briefly about these materials, these fluorophore materials, because they're not only used in these things, but they're also used in organic solar cells, but also in displays and things like that. So we should mention them. There are various flavors of them. Most common ones are organic dyes, things like rhodamine, DCM, coumarin, and all these things. Of course, these are very commonly used as food dyes, right? Food coloring and things like this. Coumarin is a good example. And they can come in all different colors. They're also used in biology quite a bit. So if you do fluorescence imaging, you find all these things. Number two is what I call quantum dots. Quantum dots have the advantage that they are very, very, very stable compared to organic molecules. They can exist for years under sunlight with no degradation at all, okay, if they're properly synthesized. What are quantum dots? They're very, very, very small particles. Not sphere. They can be spheres, but they don't have to be spheres. You can think about them as nanocrystals, primarily in organic compounds like lead sulfide, lead selenide. Their absorption and emission spectra can be tuned not only by the material property, but also by the size. The quantum yield is somewhat lower, 30% to 50%. They are generally more expensive because they require a more complicated synthesis process. Their photostability can be quite good. And this is an example of a glass with quantum dots in them. Like I said, they're being used in displays and so on nowadays. And you can access a wide variety of colors. So this is really nice for displays because you're not just doing red, green, and blue. You can do very, very complex palette of colors. So you can get very nice gamuts for your TV or whatever. You know. A third class of materials are what I call rare earth materials. These are traditional laser dyes. You know, they are inorganic, so they last forever. Things like lanthanide ions, neodymium, ytterbium. These are very commonly used for lasers from the 1960s and 70s and so on. They have very low reabsorption because of their narrow spectra, have very high quantum yields, and obviously almost infinite photostability. So those are the possibilities for the molecules. The host materials themselves, there are lots of options as well, just to be aware of course, glass, PMMA is plexiglass. Now you can also think about the shape of the device, which you mentioned, which can be useful for increasing concentration and so on. Typically, of course, you use rectangular sheet, it produces non-uniform edge illumination in the sense that if you think about what happens, this is getting concentrated here. What happens at this corner as opposed to this edge? This corner, you will expect light from both sides and have essentially a hot spot. So hotspots are obviously not very good for solar cells, so something to keep in mind. You can get circular shape, for instance, for best uniformity, but very hard to have circular cells, right? rectangles can be flexible. Hexagon can be used to tile a plane. So some examples there. Okay, so these are the all I really wanted to say about the luminescent concentrators for solar cells. I want to talk about two more ideas which are outside the solar industry, but just so you're aware of what's happening. One actually, of course, yeah. So actually, this I forgot. So let's actually look at this video. So as I said before, these are really cool because these ideas can be incorporated into glass, so they can be building integrated. So this is some more recent work from Michigan State. So I'll just play the video here. Just a minute or so.
I'm here on the waterfront in Detroit, and I'm talking about solar power. When you think of traditional solar panels, you think of those large black squares that are mounted on rooftops or in fields. But what if we were able to start getting our solar panels to look like this? An entire skyscraper dedicated to harvesting solar energy. A Michigan State professor is making that happen right now. I'm sitting here with Professor Lunt, a professor in the College of Engineering.
Correct. I'm a professor of chemical engineering and material science. When I was growing up, I grew up just outside of Boston, and I began to appreciate the amount of area there is in not only glass, but just tall buildings in general. And there's often more area in the vertical footprint than there is in the rooftop footprint. One of our thoughts was if we could turn these areas into solar harvesting surfaces, we could really make a big impact. This is a transparent luminescent solar concentrator. The way that this works is it's going to capture the parts of the solar spectrum that you can't see with your eye. So it's going to capture the ultraviolet and near infrared parts of the solar spectrum, and that glowing infrared light gets guided to the edge of the glass, where we mount very thin strips of solar cells, and that's going to convert that energy into electricity. So now we are in the molecular and organic exophonics laboratory. And so this is a fully assembled prototype of this type of technology. So I guess what we can do at this point is just hook this up and show you kind of how it works. So what I'm going to do now is just hook up the solar concentrator, and then we're going to shine the light onto the active layer. And the fan moves.
Generating power.
That's right.
So with much bigger windows, with the actual power of intensity of the sun,
that's right.
You're going to do more than just be able to move a little fan.
That's right. We're going to be able to power the building. Any building can start to be a good solar collector now. So we can turn our solar farms into solar cities.
When you're looking at a building like this, if we implemented your technology on this, how would this building look different?
So the building will look exactly the same.
Just be normal windows.
That's right.
That's the benefit, right?
That's right. And whether you're talking about the windows or the siding, the building will look exactly how you want the building to look. And you won't even know that the solar technology is there.
Is this something that could be retrofit onto old buildings?
Yeah, that's actually a very important part of this technology, is we actually have the ability to not only integrate it during the window manufacturing process, but we can also make laminates where we can retrofit from the inside of the building. And so this type of technology allows us to really think about new construction as well as existing construction, but also other applications such as mobile electronics, automobiles, greenhouses. So the applications are almost endless. We have glass up there, we have glass down here. Because we've developed this really scalable process, this really scalable technology, I think we can start to see this within a couple of years in products. So that's our goal, is to see products in a variety of areas within the next couple of years.
So this isn't some far-flung thing. This
is happening now. Yeah.
Okay, so get an idea. So this is a very interesting paper that came out 2 years ago from Facebook Connectivity Labs, based in, I think in California or in Seattle, I don't remember, but they are using a solar concentrator, not a solar concentrator, a luminescent concentrator for free space optical communications. So let me first, before we explain what this is, let's explain what they're trying to do. They're trying to get internet to rural areas, anywhere in the world, like Africa, Asia, and so on. That's the idea. They want to beam internet. This is the eventual vision. And the idea here is to use laser beams for line of sight communication to do data communication. The idea would be instead of having cell towers talk to cell towers, you can have laser beams between one tower and another tower, or in the case of Google, you might remember they had this idea of balloons beaming this laser light. They're doing something similar as well. Okay, this idea. So laser beam to laser beam. Now think about what they're trying to do. You're trying to send a tiny laser beam kilometers away and capture it on some detector, right? So what does that mean? If you are a detector sitting and looking at a laser beam, say several kilometers away, and you might be, shaking in the wind or vibrating or whatever, right? You have a tiny little beam. How are you going to capture it? Because you're moving, right? In the case, if you're airborne, you'll be, wind and so on. Very challenging problem. Okay. So their idea. So what are you trying to do? You're trying to collect light from a faraway source, and it can come from any direction. You ideally want to collect it from any direction because you can have a transmitter from here, transmitter from here, wherever. So you want an omnidirectional collector. Okay, this is where the concentrator comes in. So they're doing is basically using a concentrator very similar to what I've drawn here. Light's coming in, shown in blue from the top. It's absorbed by some molecules in the sheet. Okay, in this case, it's not really a sheet. It's you'll see some pictures. Oh yeah, the picture is here. It looks like that. It looks yellow because there's some organic molecules in here. They absorb the incident light, they re-emit, and the re-emitted light is trapped in here, and it's simply slowly kind of funneled into a fiber. Then you can do all the other data processing. Okay. So here you see the fiber and some collimation optics, and then you have a photodetector. This is a silicon avalanche photodetector, so you can get the signal. This converts to electronics, right? Digital signal. And here you see what's happening. The blue light comes in, molecule absorbs it, emits in green. Some light is escaping, most of this light is collected. So the reason they're using this because it's relatively cheap, and it doesn't need to be pointed at the source, right? The light can come in any direction, it'll still get absorbed. This is the key idea. And here you can see the same plots as I showed before, right? You have an absorption in this blue. So this is the blue, emission in the green. Okay. Then this is what's detected by the silicon APD. This is the signal coming in from the laser. Okay. Yeah, more details of their system. So this is their laser. It's a blue violet laser. It's collimated, and this is far away, kilometers away, let's imagine. In their experiment, I think it was closer. And that's our little LSC concentrator. And the light's collected here onto the APD, and you measure on a scope. And they showed very, very fast communication. Of course, the reason you're using laser versus telecom or the cell phone signal is because of bandwidth, right? Laser has much shorter wavelength, so you can pack a lot more density of information. You can go a lot faster, gigahertz, okay? Hundreds of gigahertz in principle. Okay, so this stuff is okay. They, in addition to this, made something like a sphere. So they took all these things, whoops, and built little sections of it in a big sphere, so light can come in from any direction. They showed omnidirectional, and all of that light gets funneled into this little fiber with some lens here onto the APD. And this is the photograph of that actual device. It's glowing because it's fluorescent. So this is an actual application outside solar for communication. This just came out, I think, in 2016 or 2017. So very active area of work. The last application I want to talk about is in agricultural lighting. This comes from some work done by a company in New Mexico, Los Alamos, QD. Now, of course, QD stands for quantum dots. So in this case, they're trying to, this is the goal. So they have a greenhouse with plants growing. In this case, it's tomato, but you can imagine more expensive things, marijuana, for instance. That would be a very big cash crop. So here, what they're trying to do is they're trying to optimize the illumination spectrum to what makes the best, most efficient photosynthesis, for instance. Okay? So you see these fiber lines going down here? That is the emission going down to the tomato plants. And you see these yellow things here? That is a collection. Okay, so that's a concentrator part of it. It's illuminated with blue light. It emits, I don't recall exactly, we'll see, orange, I think. That's why it looks orange, which goes to the tomato plant. That's the idea. Now you can very precisely illuminate them, precision agriculture. So they have lots of different, very interesting kinds of architectures here. So you have a hollow core fiber with a quantum dot mix. So you have a white LED here, or blue LED, illuminating a fiber, which has mixed in it different quantum dots, which is like these little dots that just like these molecules. And they emit all these wavelengths. For instance, you can mix all these colors. You can have a hollow core fiber with segments of quantum dots, so you can see different sections of the fiber have different types of quantum dots, again, resulting in the same emission. You can have a hollow core fiber. Hollow core just means it's open in the center with segments of quantum dots, illuminated from the top with LED, just a flashlight. Okay. And this is the same kind of thing, but with a concentrator. It's a luminescent concentrator filled with quantum dots, illuminated from the top, and the emitted light is collected by fiber and it's emitted, which is exactly what they have here. Okay, and this is a close-up photograph of the system. These are the luminescent